Hello and welcome to sections 4.1 and 4.2. We're kind of condensing this into one section, skipping a few of the things in 4.1 and 4.2. A lot of that was covered in the appendix G.1 and G.2 stuff, so we're going to make this a little bit shorter here. So first off, what chapter 4 is all about is power functions. So what is a power function? A power function is a function that can be written in this form: y equals k times x to the p, where k and p are constants. So that means that the y and the x are the variables here. And some things to notice about this is k is multiplied out in front, and x is the base of the exponent. P is the exponent itself. So if you have the base of the exponent is the variable, and then there's some number as the exponent itself, then it's a power function. So let's look at this example here to look at these different functions and identify k, called the coefficient, and p, which is called the exponent or the power. So for this first one, let's see, the r is the base of the exponent and the power is 2. So as long as that variable r is the base of the exponent, and if you have any number like that pi multiplied out in front, then yes, it is a power function. The k is pi and the p is 2, and those are both numbers, so that's good. Then looking at b here, this is a little different. Now 2 is the base of the exponent, but the variable x is the exponent itself. So that's switched around. We're supposed to have the variable as the base and the number as the power, but that's not the way this one is. So this is actually called an exponential function, which is what we're going to get to in chapter 6. So this is not a power function. Okay, let's look at y equals 2x. So you might be looking at this and saying, well, okay, so you have a 2 equals k, like a number multiplied out in front, but then there's nothing written as the power of the x up here. So it turns out, well, it's actually still a power function. You just have to imagine that there's a 1 there, because this is the same thing as 2 times x to the power 1. And 1 is a number, it's a constant, so you can say that yes, this is a power function, and the k is 2 and the p is 1. Okay, let's look at part D here with this p of t function, where you plug in t, multiply it by 2, and then add 3 to the result. And now the problem is that these are not like terms, so you can't combine them into one thing. But if it's a power function, it does have to be combined into one thing times t and then to some power, but you can't really do that here because they're separate. You can't combine the like terms, so this is not a power function. Okay, this one's a little weird. So first of all, there's the square root of 16x. So what do you do with that? Well, one thing you can do is do the square root of 16 and the square root of x separately. That's one of the sort of rules we talked about in G.2. And the square root of 16 is just 4. So you can do that separately. And then the square root of x, remember, if it's a square root, you can imagine there's a 2 there. The square root of x you can write as x to the power 1 over 2. So that is a power function, actually. So square roots are fractional powers of x. So this is a power function with k equals 4 and p equals 1/2. All right, so let's look at example 2 here. We want to match each formula with its graph. And so, first of all, looking at the different graphs here, well, they have different properties, right? One thing I notice about them is that with some of them, the values of y are always positive. Like with this one, the values of y are always positive 1. With this one, the values of y are always positive or 0 at this point, but almost always positive, and even when x is negative. And same with this one here. Now with this one, when x is negative, the y also comes out to be negative, but when x is positive, y is positive. So that's one thing I noticed about this, and these ones are the same thing. The y can be either negative when x is negative or positive. So which of the graphs does that, which of these equations match with that property? Well, let's see. I'm going to start with A here. Well, x to the 0, what does that mean? Well, actually, x to the 0 is just 1. This is the same thing as just saying y equals 1. So no matter what x is, the y coordinate that you get is 1. And which one of these works with that? It's this one. This is a y equals 1. Okay, so that's that. Okay, with these other ones, you could always plug in some numbers. Like, for example, if I was going to plug in -2, -1, 0, 1, and 2 for x, make a little table here. Very little table with my smallest handwriting. Well, x to the power 1 just means x. This is just y equals x. So if x is -2, well, y is equal to that, so y will be -2. If x is -1, then y is -1. And same with the rest of these. So if x is negative, then y is negative because it's the same. The other thing is, you might notice this is a straight line. You could write this as y equals 0 plus 1 times x. So it's a straight line with, so it's basically in slope-intercept form here, the way I wrote it, with y-intercept 0 and slope 1. And the one that's a straight line is this one over here. Okay. How about x squared? Important thing to know about squaring x is that the result of squaring anything is always positive, or maybe 0 if x is 0. So which one of these have y coordinates that are positive or 0? It would be either this one or this one. Okay. Is there another one that's always going to be positive or 0? Another one of the equations? Well, let's think about C and D here. So I'm going to try plugging in a number like -2, for example, for x. Let's try plugging in -2 and -1 and 0 to think about this. If you plug in -2 into this, -2 times -2, -2 squared, is going to be 4. If you plug in -1, -1 squared is going to be 1. 0 squared is going to be 0. Okay, and what if we did the same thing with equation D here? Plug in -2 or -1 or 0. Okay, well, -2 to the power 4 means we're going to do -2 times -2 times -2 times -2. And that's a lot. So they're going to end up being positive because you could pair them up. Because if you have an even number of them, every pair of them is going to become positive. So it's going to be positive 4 and then another positive 4, which comes out to be 16. And then if you plug in negative 1, well, negative 1 times negative 1 times negative 1 times negative 1 4 times is just 1. And 0 times itself 4 times is just 0. So both of these are always positive or 0. So those are the ones where the y coordinates must always come out to be positive. But which one is which? Well, let's see. It looks like with this one, if you plug in x equals 2 or negative 2, you're going to get, it looks like about 4 right there. Okay. And if you plug in 2, you're going to get about 4. Same deal. Right. But with this one, if you plug in 2 or negative 2, it's above the graph because this one goes up way steeper. So that's got to be the one that goes with x to the 4th. So this is not exactly a parabola. It's like flatter in the middle here and then steeper out on these parts. So this is y equals x to the 4th power. And this one is y equals x squared, like a regular old parabola. Okay, so that's the difference between having a higher power of x rather than x squared, is it makes it steeper when you go on the outsides and flatter close to 0. Okay, now how about these ones? We have x to the 3rd and y to the 5th. I want to try plugging in a few numbers too to get an idea for how these work. Like let's try negative 2 or 0 or 2 here. So if you plug in negative 2 to the power 3, well, 2 of them pair up to cancel out and make positive 4. That's going to be 4 times negative 2. That's a positive times a negative. So then that ends up being negative 8. Likewise, if you just do 2 times 2 times 2 3 times, you'll get positive 8. And 0 times 0 times 0 3 times is 0. So this is one that can be negative. If x is negative, the y coordinates will be negative. So that must be one of these first two at the top. But the difference between these is one is steeper when x is further away, and but flatter in the middle. And this one is kind of a little bit more evenly smooth. So maybe you know what's coming. If you know the answer, that's great. Well, I'll verify it here in a second because I'm going to plug in negative 2 and 0 and 2 into this one to see what's different. So if you do negative 2 to the 5th power, that means negative 2 times negative 2 times negative 2 times negative 2 times negative 2. And let's see, 4 of them are going to pair up to make 4 times 4 times negative 2. That's going to turn into negative 32. So that's a really big negative number. Likewise, 2 to the power 5 is going to be positive 32. 0 to the power 5 is just 0. So with this one, if x is a bigger number, like bigger than 1, then x to the 5th gets to be really big. And that is what's happening with this one here. Like the graph is going up so steeply, it's going to hit 32 up somewhere past the top. But with this one, it's not quite as steep. It looks like 2.8 is going to be about up here. So this one is F. Well, no, I'm sorry, E is what I meant to say. X to the power 3. This one is F. Okay, so the point of this exercise is to try to develop some understanding of how the power of x affects the shape of the graph. If the power of x is an odd number, then you're going to have negative y coordinates when x is negative. And if x is, sorry, if the power is an even number like 0 or 2 or 4, then the y coordinates are always going to be positive. And the bigger the power is, the steeper it's going to be when x is bigger than 1 or less than -1, and the flatter it will be when x is close to 0. Okay, so we'll go on to examples 3 and 4 in the next video. See you then.